Hello and welcome to the FEA tutorial. In this video, we will focus on the nonlinear analysis, specifically the material nonlinear. Nonlinear analysis is one of the most challenging simulation in FEA. The material nonlinear is often associated to the large deformation, and the material properties will be not a constant anymore. For example, in the structural analysis, the Young's modulus is changed as the strain increases. So the Young's modulus will be defined by the stress and strain curve, which will be obtained from the experiment. This nonlinear demo is still from the NAFAM benchmark model example. As you can see from the picture here, it's a cantilever beam. One end is fixed, the other end subject to the bending moment about the neutral axis. The bending moment is not a constant as well. It is defined by a step function. The time span is 2 seconds. The period from 0 to 1 second. The torque is only 2,000 pound-inch is in the imperial unit. Under this low torque, the material is in the linear stage, and the deflection can be calculated by the analytical solution, which is about 2 inch. And after 1 second, it has a step change to 7,000, which will cause the nonlinear behavior for this cantilever beam, and the deflection at the free end will be about 7.5 inch according to the analytical calculation from the NAFAM benchmark. The material properties are given here. The stress and strain curve will be defined by this table. The Poisson ratio is defined as 0. So the dimension of this beam are given here. The length is 100 inch, and the cross section is 2 by 1 inch. So this is the description of the problem. We can start the Solidworks to build the model. So I will start from creating a new part. This is the imperial unit, so I will need to change the unit. So go to the tool menu, find the option, then document property, find the unit and change to the IPS. That's the imperial unit. Okay. So I will start from the front plane to create a new sketch. Draw the cross section first. So it's 2 inch high and 1 inch width. Okay. Then extrude this sketch to 100 inch. So this is the geometry of the cantilever beam. One end of this beam will be fixed. The other end will apply a torque about the neutral axis. To define the torque on this end, we will need to create a reference axis. So I will select this surface, or we can just define the reference axis directly from the plane. Let's see, we can choose front. We can choose. No, that's not the way. So I still need to draw a line on this surface and then create the reference axis based on this line. So I'm going to draw a line, connect to the two midpoint of these two edges, and access the sketch and create a new reference axis. which is based on this line. Okay, so we have a reference axis to define the torque on the free edge. So we can go to the simulation tab and then create a new start it. Select the nonlinear and give it a name. Nonlinear. Okay, to accept it. We just need to follow the standard procedure of the typical FEA simulation. So right click the part and then apply the new material. You need to create a new material. So in the custom line, I'll create a new categories for it. Nonlinear. Under this category, we can create a new material. Default nonlinear. And in the model type, we can change the linear elastic to nonlinear elastic. The unit is IPS, that's correct. And here is a button, create stress strain curve. Is a table. So there are two columns here. Column A, you can define the strain on column A and stress in the column B. So when the strain is 0, the stress is 0, of course. And double click the point 1, we can insert a new row. When the strain is 0.1%, then the stress is 3000 psi. Double click again to insert a new row. When the strain is 2.001, the stress is 60.03 mega psi. It's 60.003 actually. So we need to type one more 0 here. Okay, so the stress strain curve has been defined in this table. Can apply and then close the windows. The new material has been assigned to this part, and we can define the fixed support on the free edge. So I need to change the view to get a better view. Rotate a bit to select this surface to fix it, and also select this surface to define the torque. You asked to define the reference geometries to define the torque, so we just need to go to the axis as a reference geometry to define the torque. Look at the arrow of this torque. We change the unit to English and type 1 here. I will come back to this later to explain why we define 1 here. So the torque is defined by the step function, which cover 2 second periods. From 0 to 2 seconds is 2000, and from 1 to 2 seconds is 7000. So we will go to the variation with time and select curve and add it to create this step function by this table. So from 0 moment is 2000, and 1 second is 2000 again. It's a step function, so in a very small time step, for example 1.001, the value change to 7000. I double click the point 3 again to insert a new row. At the moment of 2 seconds, it remains 7000 again. So that's the step function. We can view this step function to see it in clear detail. I can close it, the button OK. So this step function will multiply the value here to define the torque. That's the reason we define 1 in this cell. OK. The total time span is 2 seconds. So we'll go to the root of this simulation tree, right click and select the properties. You can see in this window that the default time period only 1 second. So we need to change to 2 seconds. Select the button OK. So everything's ready. We can create a mesh and then run the model. Close up the window, just hit the button OK. It's a nonlinear problem, so you can expect that it will take a bit longer than the normal linear problem. But this is a very simple nonlinear problem, so I think it will take probably about 1 minute to solve the model. Okay, it's done. Yeah, it's around 1 minute to solve this model. If you are using a laptop, you can expect it's a bit longer. In the NAFEM benchmark, it gives the diffraction at the free end, at the linear stage and the nonlinear stage. So we can see from this part, this is the final step of the result. The time is 2 seconds. It's nonlinear stage. To view the diffraction, we go to the displacement, double click it. The result, look at the legend here, the unit is millimeter. So you can right click and then add this definition. Change the unit to inch and the item to look at the coordinate system here. The deflection direction should be Y and then OK. So we look at the legend again. The maximum or minimum doesn't matter. The symbol, the minus symbol represents the direction of the deflection. So it is 7.4, about 74 inch. Let's see the analytical solution. That's 7.5 inch, which is very close. It's about a 1% difference, which is not so bad. And then in the linear stage, the deflection is 5 inch. You can go back to the Solidworks and change the time step. So we can go to the 1 second, which is the linear stage, and OK. So the value here is minus 4.977, which is very close to the analytical solution. So I hope this demonstration can give you an idea how to perform the material nonlinear in the Solidworks simulation.